It's about a quarter of. So you need to chew up about 5 minutes by when you start. Whenever you start, tell me when you do the introductions. Yeah. That's always a good thing to do. Ooh, no pink boxes.
No, you have to make sure you don't go too much.
No pink boxes. I can't use the stay in the pink box or else slide from Honolulu.
No, they have not put them up yet, so.
Oh, you think there will be pink boxes?
I think so. Hi, everyone. Is this on? Do you hear me? Yes, I think. Is this on? No? No. Kinda. It's kinda on. Hello.
Yeah.
Shout.
Get very friendly with the mic.
Yes. Yeah, we just talked about this during the newcomers tutorial that people like tell you, eat the mic, get closer. My name is Mirjam Kühne, not Mirja Kühlewind. This is very confusing for people. Sometimes you get emails for each other. I'm not actually giving this presentation. I am a member of the educational team that's responsible for organizing these tutorials, like the newcomers tutorial that some of you have been just now next door. There was another tutorial here in the room. We usually give 4 tutorials on Sunday before the IETF meetings. This is one of them. And that's an overview of the transport area. So we always give a newcomers tutorial. We usually also give an overview tutorial of one of the areas. So there are currently 7 areas, and transport is this time around giving a tutorial and giving an introduction on what's currently happening in the transport area, and next time there will be another area, and so forth, until like in 7 meetings or so, transport is up again. And then there is another tutorial in parallel here now. Oh yeah, that's on how to write a good RFC, but apparently you're not interested in that, so that's for next time. So we're always rotating this. We're having different topics each time, and from time to time we're also repeating some topics that might be interesting for a wider audience. So if you have any suggestions for topics or any feedback for us, there's a list. There's the edu team at IETF.org. There's also some information about the education team on the IETF website, and all the tutorials are always listed on Sunday. On the agenda for Sunday, they're always on Sunday afternoon. We're also responsible, so in our portfolio, we also have some other activities like the mentoring activities that maybe some of you have teamed up with a mentor or mentee. The quick connections kind of get together for newcomers that's happening this afternoon. And one other activity is some training for and information sharing with working group chairs. So there's always a working group chairs lunch training session that the education team is organizes. And it kind of falls into a bigger education and mentoring directorate that we're organized in, and it's kind of under the general area. So I'm trying to kill some time here because Mirja is coming out of a meeting that she's held up with because she is also on the ISG, right? Yes. She's a transport area director. Yes. So you have actually the area director telling you what's happening in the area. That's wonderful. But Dave can start, I think, and then Mirja can come in and take over. Unless you have any general questions about education team or any feedback you want to give to me, you can also find me during the week. All right, then it's yours. I think it wasn't quite 5 minutes, but
Good enough. So good afternoon. Thank you for coming. My name's David Black. I'm one of the 2 presenters. I'm with Dell EMC. I've been involved in IETF and transport area for over 20 years at this point. I work at Dell EMC, mostly on storage. You'll find my name, for example, on the most recent RFC for iSCSI, one of about a couple dozen RFCs I've written. I'm a chair of the Transport Area Working Group and another working group in the Transport Area. And so Miria, who will be here in about 10 minutes or so, and I are going to do an overview of the transport and services area. And with luck, my first piece will take long enough that she'll be walking in at about the point where her first slide comes up. So the TSV area is often referred to as just transport. It covers a range of technical topics related to data transport in the internet. Primarily protocol design and maintenance at layer 4, and I'll show you in just a minute what we mean by layer 4. This is TCP, UDP, SCTP, and friends. These are the protocols that live at that layer. Major technical concerns at this layer of the protocol stack are congestion control and active queue management. Transport started out, big concern was to prevent congestive collapse of the internet. Been there, done that, not going back again. Well back in internet history, hasn't been a concern recently. More recent concern is queue occupancy and in particular buffer bloat, about which quite a bit of very useful work has been done recently. Transport also covers quality of service and related signaling protocols, QoS. Two examples are differentiated services framework, usually called DiffServ, and the RSVP signaling protocol, sometimes called the reservation protocol. Now, there's some activities in the transport area that aren't layer 4 specific. For example, storage protocols like iSCSI are really layer 5 and above. They're located in TSV for historical reasons. As we go through the survey, you'll get a sense of what those are. It's often the case that they use a great deal of, they're capable of using quite a bit of bandwidth, or that there were concerns that were transport specific in the protocol design that were best worked on in this area, for example, dealing with certain aspects of congestion control. So here's, to show you where transport lives, here's a classic network stack you find in any networking textbook, going from layer 1 physical all the way up to layer 7 application. Transport is sitting right there. Let's see if I can get this doc to work. There's transport right in the middle at layer 4. To give you an idea what this means in practice, if you're busy looking at the web instead of paying attention to the slides, here's what your stack might look like if you're plugged into a socket in the wall. I used hardware, Cat5 cable, 100 megabit Ethernet, IP, and sure enough, there's TCP at layer 4 below the HTTP and HTML stack that the web browser uses. Now, this is what's in the textbook. This is where transport lives. And practice, two points. Layer 6 doesn't really exist. We get up to about layer 5, and then it's other stuff that happens inside the layer 5 protocol. And the other thing is that the network stack for the internet is often referred to as an hourglass stack or architecture, where IP is the thin point of the hourglass. It's a relatively simple protocol by comparison to some other things, and it allows a great deal of flexibility in what runs below it. IP runs over nearly everything. Heck, there's even a German pigeon fanciers club that got it to run over carrier pigeons. The ping time was truly impressive. And above IP, a great deal of innovation is possible because there's this interface. Now, lately, it's become the case that a lot of this sort of stability has now encompassed both the network and transport layers. So people are tending to work with one of a very small number of transport protocols, TCP and UDP. So speaking of TCP, in the beginning, there was TCP. Well, that's sort of how our story begins. Transport is one of the oldest IETF areas. At layer 4, their key internet elements, whatever you do over the internet almost certainly involves some transport protocol, TCP, UDP, later on SCTP, which was originally developed for very low latency telephony signaling, but has found a number of other uses. The most recent interesting use is it's the data channel for WebRTC. DCCP, which is an intermediate protocol that tries to do congestion control for unreliable transmissions. And the latest work in transport, which you'll hear about a bit later in this presentation, is QUIC, which is a new transport protocol that's been designed and adapted for web traffic. And that's a general theme of transport. We adapt technology to the internet, make things work over unreliable packets at large scale with congestion control. And so storage, pseudowires, and multimedia are examples of things the transport area has worked on to get to work at large scale with congestion control. Need to say a few things about multimedia and the RAI area. Once upon a time, when the internet was first put together, the conventional wisdom, what everybody understood, was you couldn't get reliable source unreliable packets unless you had some kind of protocol like TCP that was prepared to insert some serious buffering delays and be prepared to do retransmission when packets were dropped. This was disproved by the early 1990s. RTP, which is a real-time transport protocol, runs over UDP, and audio-video codecs had gotten to the point that in combination with the underlying network hardware, you could in fact do real-time audio and video over the internet, and it all worked. An example that turned everybody's heads was in 1994, the Rolling Stones were multicast on the M-Bone over the internet, and people got a real concert experience, or at least as good as you could get on the computer displays at the time. That whole area of multimedia work broadened to related work, particularly IP telephony. And IP telephony was motivation for work initially on SCTP and then on SIP, which is a session initiation protocol that's widely used for IP telephony. And all of this broadened to the point that transport was actually split into two, that all of the work in transport that related to multimedia and IP telephony was then split off to become a separate area called the real-time applications and infrastructure area. And so historically, that was transport work because it interacted very, very strongly with the transport layer of the network and concerns about traffic management, congestion management. And the traffic management congestion management has gotten mature enough that this can now be sort of pursued as a more or less separate area inside the IETF. So this is where we were hoping that Mira come in. So I will say a little bit about some of what's going on here and see if I can't chew up some time. First, are there any questions about anything I've talked about so far? All right. Let me see if I can chew up a little bit of time here. Do sort of a real quick overview. There'll be slides on each of these. So today's transport area scope is sort of summarized in these bullets. You have the core transport protocols, things like TCP, SCTP, and UDP that in many cases have been around for a long time. They're relatively mature protocols. Made some work done on them. QUIC, which is a new transport protocol with security intended primarily for web traffic. Congestion control and queue management. This is the infrastructure that sits inside the network in routers. This is where the queue management sits, and then the corresponding protocol logic at the endpoints that responds to what's going on in the routers to appropriately manage congestion and try not to overload the network. NAT traversal. NAT stands for Network Address Translation. You probably have one of these in the box that your internet provider gave you to put in your house that allows you to connect multiple things up to one internet connection. It stands for Network Address Translation because what commonly happens is the provider will give you one IP address, but every single device you want to attach to the internet via your local box wants its own IP address. And what's sitting in the middle in that box is something called a NAT. It's actually a port translating version of a network address translator. And translation is not perfect. When I go from many IP addresses to the one IP address that the internet service provider uses, certain things don't work transparently. A lot of the work in figuring out how to get things to run through these boxes is transport area work. quality of service and related quality of service signaling work goes on in the transport area. This is topics like the differentiated services QoS framework for the internet. Storage networking. A number of very important protocols that are used in distributed storage are developed in the transport area. iSCSI and NFS are two examples. And there's a whole bunch of other topics, such as delay-tolerant networking and performance metrics and measurement, where the transport area has been a logical or convenient home for that. And with that, here's Mirja, who will introduce herself and pick up from here.
Oh, great. Wow. So you were quick here. So hi, I'm Mirja. I'm one of the transport area directors, and usually I try to delegate this to somebody else, but this time it's on me. So anyway, I'm more or less qualified to tell you some more specific things about part of the work we do in transport. So I will go over the first half of these, and then David will pick up the second half again. Yeah, so transport protocols, that's like our main business. And like TCP and UDP are well-known transport protocols that has been developed in the IETF, and we're still maintaining these. I mean, UDP is not really a transport protocol, but it's still, I mean, a lot of stuff is running over UDP. So our task here is also to give advice to people developing protocols on top of UDP, for example. For TCP, we have our own working group, that's TCPM for maintenance work, and UDP usually has topics that are discussed in the TSW working group. So TSW working group, did you say something about this already?
Not much.
No. TSW working group is a working group that kind of catches up the topics that don't fit anywhere and are not big enough for our own working group. There are a couple more transport protocols actually that are less well known and less deployed, but are deployed in special use cases. One of them is DCCP, for example. The other one is STTP, and then there's of course the big new shiny one, which is QUIC. So QUIC is currently under development. QUIC was first brought up by Google, and they already deployed it on a large scale on their communication systems, basically. But what we have now in the IETF since about a year is not like the same protocol anymore. So we basically usually speak about the Google QUIC and the IETF QUIC. It already diverged a lot because you bring more people in the process, you have more opinions, and hopefully that also helps to improve the proposed protocol. The difference between QUIC and all of the other protocols you've seen on the previous slide is that QUIC has encryption integrated inherently from the beginning. So all QUIC traffic will be encrypted, and the encryption uses the TLS protocol. So that's also a big difference from the Google version of QUIC, which is also encrypted but uses an own crypto protocol basically. And that's also one of the big discussions that are happening currently in transport. What does this change to all encrypted means for the traffic, for the operation of the internet? Okay, to go a little bit more into detail, because that's one of the big topics. So if you look at this picture, what you have today basically, and I have to say HTTP is the main use case for QUIC, but QUIC is a general purpose protocol. So currently the working group is really focusing on making it work for HTTP, but it's not the only use case. So today you have HTTP, hopefully HTTPS over TLS over TCP. And with QUIC, one of the big benefits for HTTP traffic is that this purple box here, the multiplexing, is moved into the QUIC protocol. So that actually provides you a performance benefit because you don't have any head of line blocking anymore, which you still have in the old modem. The other big difference, what I already mentioned, is that the green box is not a layer anymore. It's really within QUIC, and there's a lot of interworking between QUIC and TLS. Yeah, that's also the more RFC style for you right-hand diagram, which shows you what the interconnection between the crypto part in QUIC is and the QUIC transport machinery, basically. Yeah, so beside hand of line blocking, one also big difference for performance is that it actually reduces latency. And with TLS, you already have a quicker handshake, basically. So you have something which is called session resumption or zero RTT, which means if you have talked to the server previously, you can rejoin your session and like send encrypted data from the beginning without the handshake or like without waiting for the completion of the handshake. Due to the integration of the encryption into TLS, you even save the transport handshake. The crypto handshake is combined with the transport handshake, and you can start sending data to a resumed session right from the beginning with the very first packet. So basically, you send out your first hello to the server, and you immediately send out your HTTP request as well. And then as soon as the server has calculated the crypto context, it can send you the data you need. Okay, related to all this work, not quick and specifically, is a work that's happened in the TAPS working group. TAPS stands for Transport Services. And the idea here is, or the question here is, how can we use more effective use of these different protocols, including quick? Because today, if you want to use a different protocol, you actually have to basically change your operating system because it gives you kind of two options, either TCP or UDP. I mean, the other interfaces are there, but nobody is actually requesting them. So the idea here is really to change the interface in a way that it makes it possible for the operating system to select the right protocol for you, for your needs, for your application, but also that is working on the path. Because sometimes you have a situation where one protocol is actually not supported by the path, where packets are blocked. For example, UDP is blocked in a lot of cases. So you cannot use UDP-based protocols. For Quick specifically, you see this case that today when Quick is implemented, which works over UDP, you always have a fallback to TCP. So basically, depending on how it's implemented, you either send out like 2 connection requests, and the one that gives you back faster is the one you select, or you wait for a while. If Quick doesn't work, then you try to connect with TCP and run everything over TCP again. Yeah. Okay, connected to transport protocols is a very important topic, is congestion control. So congestion control is, the main purpose is basically, or it was invented when there was a congestion collapse in the late 80s or beginning of the 90s. So the goal here really is to kind of let the internet run safely. Don't destroy the internet, right? So of course, congestion control also tries to maximize your throughput and tries to get the most out of the connection you have. But like when we all in the IETF discuss congestion control, really the safety point is kind of in focus. We don't want to write something down in our specs that can break the internet. So that's also kind of part of the transport area for work that we're kind of monitoring in the other areas, is like trying to figure out if the work that's done in those areas is safe to deploy with respect to the load that goes on the internet. I can go on the next slide for that one. We have very few congestion control schemes that are documented in RFC. Basically, it's like New Reno, which is the original proposal. And like since a few months, there's also an RFC that describes cubic. And that is because we only put something down, as I said already, when we know it's safe to deploy. And for congestion control, it's really hard to figure out if it's safe to deploy if you don't deploy it, if you don't have it deployed yet, right? So for cubic, this is in use for, I don't know, more than 10 or 20 years. So that seems pretty safe. For new proposals, it's really hard to say something. However, what we do have is that we have also research groups connected to the IETF. Those research groups are part of the IRTF, of the Internet Research Task Force, but are co-located with the IETF, so folks see each other, can talk to each other, and go to the meetings. And there, if you have a new congestion control, that's the right place to go to and get feedback and discuss this. And also the IRTF groups can publish documents, of course. Yeah, but I mean, in general, we have this long-lasting question about where to do the work on congestion control, and it really depends on a case-by-case basis where we put the work at the end and which working group. Current activity, so in the Internet Congestion Control Research Group, the ICCRG, we see a lot of presentations from Google again on BBR. So that's a new congestion control that they are already using in Quick and is discussed a lot here. Also, concerns about deployment and stability are discussed. And the other part where we have congestion control work right now is the RMCAT working group. And that is focusing on congestion control for real-time media, because that's really a special case, because you have the media decoder that might also adapt the rate, so you have some interactions there, so that's like a hard case, and it's a little bit a research group, but it's part of the IETF because we have a real problem that we need to address here. The other part of congestion control is what's happening in the network. So basically, how do you know that there's congestion in the network? Today, you know this mainly by seeing drops. And those drops usually happen when there's a buffer in the network that overflows and then a packet is lost. You assume it's congestion, you reduce its sending rate. So to get a little bit ahead of this buffer overflow, AQM is what you need basically. So you watch the queues in your router, and when you see that your queue is filling, you drop a few packets early on, not too many. So you give some feedback to the endpoint, and the endpoint can reduce the rate, and you avoid the congestion before it's actually happening, before it's completely overflowing the buffers. We used to have a working group on this one because in the last couple of years, more and more schemes have been proposed, and we also wanted to standardize them so we can support, or we can advise people to actually deploy those mechanisms, because it's beneficial to have those mechanisms and not have like this burst packet loss when your buffer overflows. Even better gets the situation when you use ECN, because in this case, instead of throwing away the packet, you actually just mark the packet, and then the endpoint knows about it and can reduce the sending rate without losing the packet. However, the deployment story of ECN is a little bit more complicated, because it's not only the router that needs to mark the packet, it's both of the endpoints that need to understand this marking. So the sender, of course, has to understand the marking because it has to reduce the sending rate. And the receiver also has to understand the marking because it has to tell the sender that it saw the marking. There is some ongoing work. So ECN was standardized in 2001, I believe, so a while ago. There were some initial deployment problems, so it was never large-scale deployed, but there is some work from companies pushing deployment of ECN currently, so we hope that we see more deployment in future. Another thing that supports ECN deployment is that you can actually do better with ECN. Effectively, you don't have to use the same congestion control as you use today. You can actually optimize for the AQM mechanism that use ECN, because you can provide a very early signal without any disadvantage, right? Because you don't drop any pockets. You can provide much more feedback than when you want to do it on a drop base. With drops, you always try to avoid packet loss. With ECN, there's actually no reason to avoid the congestion feedback if you are in congestion, right? You can send as much feedback as you want, as long as the situation is under control. So what you need is, however, if you send different kind of feedback, is also a different reaction. So there is this example of data center TCP that was actually doing exactly this. You provide a different kind of AQM in your data center, and you react differently to it, and both together optimize your network and use it more efficiently. And we try to achieve the same thing in the internet, basically, but those two different schemes cannot really coexist on the same connection. So what we do is we try to put them into different queues. One queue is working the traditional way, maybe drop-based, maybe ECN-based, but it's in both cases the same feedback you get. And the other queue is giving you much earlier, much more feedback you can react to quickly in a different way. Yeah, and there's a picture for it. So what it means is, in the first picture here, this is the traditional way you do it. So basically, when you get a congestion feedback signal, you halve your sending rate. And to maintain your link utilization, you have to have a number of packets in your buffer to actually cover this period where you just have less packets sending. If you would now just change your AQM mechanism and give you very early feedback at a low buffer rate, then that means you still have your sending rate, and at a certain point, you don't have enough packets to send anymore. So your utilization would suffer as well. And what we really want is give you a very early signal, you only reduce your sending rate a little bit, and the link is still fully utilized, which is the third picture. And maybe this is a good point to ask for questions. Do you have any questions on this part? Yeah.
Thanks. My name is Saulo. I work for the International Civil Aviation Organization. It's just, if I don't put the question now, I will forget for sure. So just one question, you talk about congestion, and with the forecast, like we're gonna have more millions or billions of devices connected. And so do you have a work in the transport and services area or to forecast and to see when the bottleneck will be happening that you're scared to solve, or there is no such work going and we solve the problems as they appear to you?
You mean forecasting the congestion?
Yes. Based on the number of devices to be connected in the future.
So I'm trying to make my head up how that could even work, but it's really hard in a distributed network like the internet to actually try to forecast anything, right? It's like it's a tons of distributed endpoints connected, and the traffic is routed in a way that you might not see on the transport layer, right? So I don't even know how that could work. I guess in this case the answer is no.
For the most part, the congestion control mechanisms that are used are scalable. They have scaled over several orders of bandwidth increases in the internet, and by and large are still working relatively effectively. Scalability is absolutely a design criterion, what's shown on the screen right now. And so it isn't so much a matter of forecasting when things are going to break, it's a matter of designing things up front so that the forecasting of when they're going to run out of steam isn't necessary.
You're on the next
Okay,
slide.
next slide. Yep. Okay, so I'm going to pick up the rest of the transport area scope and describe things starting from NAT traversal. NAT traversal, NAT used to be a dirty word around here. The IETF originally believed that we ought to be able to have an IP address for every single device, and they should all be able to communicate with each other. That hasn't worked out so well. 32 bits turned out not to be enough address space for IPv4 addresses, and there are other reasons to do things like to do address translation in boxes at the edges of the internet. NATs are now widely deployed. At first, the traversal for the network address translation was done on a protocol by protocol basis. IKE, which is the key negotiation setup protocol for IPsec, was the first for which work was done. Now is a protocol independent framework consisting of the stun, turn, and ICE protocols. The basic idea behind these protocols is pinhole punching, which is that I have an application running on end system behind a NAT, and it needs to use a port. And so what happens is a pinhole is punched for that port or that session, actually, so you know what the ports are at both ends. And that pinhole is kept open via keep alive traffic as necessary so that the application can do it. The protocols involved in this are called stun, turn, and ICE. Stun involves address discovery so that you can come through a pinhole and figure out what the contact addresses look like. Turn is a relay protocol because it's sometimes necessary if I have NATs at both ends of a connection to do a relay in the middle. And ICE is an overall negotiation framework to use these. These all have RFCs. RFC numbers are on the slide. There's an ongoing work to do some improvements to turn, security improvements, some auto discovery, better IPv6 support in the TRAM working group. Quality of service. General quality of service frameworks are in the transport area. This used to be an area with a lot of work. Integrated services was the first attempt at quality service back when I first joined the IETF. It did what it was intended to do, but was per flow. You needed to have state for every int-serve flow in every router participating in that flow, every router that could potentially be a bottleneck for it. And the result was very poor scaling. And so we've moved to something called differentiated services that puts a traffic class in the IP header. We have the problem the other end of the spectrum now, which is that there are a limited number of traffic classes that can be used. And there are additional variants in QoS frameworks. One example is pre-congestion notification, which does capacity management for real-time non-congestion responsive flows. QoS signaling, the one protocol that we have and have had for quite some time is called RSVP, the Resource Reservation Protocol. Today, it's mostly used for traffic engineering. We don't see much RSVP for end-to-end traffic. And the upshot is, which is the theme coming across the slide, is most work I've described is pretty much completed. There's limited development and maintenance of diffserv and RSVP in the transport area working group, TSVWG. One of the things that is going on right now is improving support for what's called scavenger traffic, or the ability to send traffic that you would like to have less treatment, lower effort than best effort traffic. Storage networking. A lot of work is done on the IETF. iSCSI and the fiber channel over TCP protocols were developed here in cooperation with the storage standards body shown on the slide. This was done in the storage maintenance working group, which has now concluded. For NAS storage, NFS, network file system, NFS v3, and then particularly the current version NFS v4 were developed in IETF. The current version is NFS v4.2, close to complete, and the other most common file sharing protocols, the Windows, CIFS, and SMB protocols, are not developed in the IETF. There's an RDMA protocol suite called IWARP, done the RDP working group, also concluded. RDMA stands for Remote Direct Memory Access. This is often used for storage protocols. I'm involved in some new storage protocol work outside the IETF that makes extensive use of RDMA. Delay tolerant networking. So how do we communicate with over IP to the Voyager probe, which is way the heck out beyond the solar system? This is what the delay tolerant networking group is trying to solve. Deal with very high delay, low connectivity environments. All kinds of examples shown here. There's been a set of protocols defined. The two most important, which are bundle and LTP. The DTN working group is working on updating these protocols based on implementation experience, some support for new use cases, and standards track work. Finally, another topic, network performance management. The IPPM, IP Performance Measurement Working Group, sort of goes by sort of the credo of you can't manage, you can't measure. And so that's all about putting in support to measure things on the internet, standard metrics, methods to improve metrics. Current work is the measurement version of what I would sometimes call, what security people might sometimes refer to as a known plain text attack. You deliberately inject measurement traffic into the protocol you want to measure, and then observe from the internet how the protocol reacts to it. This is being used in part to do in-band OAM, so that you can be absolutely certain that the measurements used for operation administration management are coming from the path that the traffic took, because the measurements are actually embedded in the protocol that transmits the traffic. This has become an increasing concern because there are a lot of opportunities in the current internet for flows that you thought were taking the same path to not take the same path at some point. And so now I'm going to turn this back over to Mirja to talk about a new hot topic. What happens when you encrypt the headers for all these wonderful transport protocols?
Yeah, so this is like a higher layer topic that is widely discussed basically in the whole IETF, but it's very closely connected to QUIC, because that's where we encrypt everything, also information that is in the transport. And I give you a quick introduction about the discussion there maybe, and then we go on the details about what's happening this week, right? Yeah, good. So basically where we started off, kind of nothing was encrypted, everything was visible to the network. You have in this picture at the bottom the payload, because this is kind of indicating the different headers you will see on a packet. So you could even see the payload. You can see the application layer headers, so the HTTP headers, for example, and in this use case, you can see all the information in the transport header. So everything that's in the TCP header. The UDP header is a little bit smaller, doesn't give you as much information. And of course, you can see the IP header, which you also need for the routing information. So basically, even so, only the information in the P header were initially meant for the network. What happened, because everything was visible, was that some of the information provided in this header was utilized by different network functions. So yeah, I mean, basically, you have a lot of information in the transport, in TCP header specifically, that is meant for end-to-end operation. But when you look at the data, you can also do something else with it. So for example, if you match up the sequence and the egg number, or you even look at the TCP's timestamp option, you can use it for round-trip time measurements of the flow you're looking at. So that's really helpful for you, for your troubleshooting, for your network monitoring purposes. In some cases, there are also boxes in the network that would change these bits. So for example, the initial sequence number is sometimes, to stay with this example, is sometimes overwritten, because that gives you a field where you can put additional information in. Or if you, for some reason, don't want to support a certain TCP option, you can actually just strip it from the TCP SYN and it will not be used. There are other use cases where you have a good reason to rewrite stuff as well. So what we see more recently is that we have a increasing deployment of HTTPS or TLS in this case. So what this changes is that you cannot see the higher layer headers anymore. You cannot see any HTTP information anymore, but you can still see the transport layer header, which were still not meant for the network, but still provide sometimes very useful information. However, if you modify and change these things, that can also sometimes have a negative impact. For example, even if you as network don't want to support a certain TCP option, like it might never get deployed, right? And we developed it for a purpose. And there are also privacy implications. So, for example, the timestamp option is a good example. You can actually basically, if you look at the timestamp option, you can match up which connections belong to the same host because they have the same clock drift, for example. These kind of things are also critical. What's not possible anymore in this case is, of course, deep packet inspection. So why is it so horrible, or why do we actually want to encrypt more than this? And there are two good reasons, which I kind of already mentioned right now. One is really privacy concerns, but the other one is also ossification. So we have had, especially in the transport area, a lot of discussions over the last couple of years where we wanted to change something, and then the discussion ended up in, no, you can't change it because there's something deployed in the network that will not interoperate with this, that will drop packets if you change this bit, or you have to have a fallback if this option gets dropped from TCP. So it really made our protocol development more complicated, and sometimes it's even impossible to innovate on the protocols anymore. So it does help us also in the process if we try to at least secure this information in a way that we can still change the meaning and modify it on an end-to-end layer later on. The second big point is really privacy and fingerprinting. So actually, this will not be fully solved by just encrypting some of the transport information, but it's one step in this direction. So what we have in Quick basically right now is that you still have something like an outer transport header, which provides some information to the path, kind of for some information on purpose, other kind of information you cannot really avoid it. But you have also a lot of the information that was previously in the TCP header in the encrypted part of the packet. So that is kind of the inner transport header that is not visible to the outer anymore. And so basically what came up as a term that might be interesting for you is also called wire image. So what's visible on the path. However, this wire image is usually also secured, like protected in a way that you cannot modify it anymore, which is also important for the first goal, for the ossification goal, where you still try to be able to modify things. So that might be, this is at the bottom, these are two individual drafts currently, but they are discussed in the IAB and the Internet Architecture Board to give guidance on this discussion. One is called the wire image, explaining what this term wire image actually means, what is covered by the wire image. And the other is talking about explicit path signals, so making or taking more a look on when we develop a protocol, what should be provided to the path and what is useful for the path to provide. Yeah, I've shown this. So yeah, the main part of the discussion that's ongoing that you might ask yourself in the meantime already is like, what happens to all the devices that actually have been using this information, that have been modifying this information, that have been providing services that we still want on the network? And this is a discussion that's also happening in the IETF, and I don't have an answer for you right now. But like, we are aware of these things, and we need to figure out what we need to support, what information we need to provide, and how we can, on the one hand, we can improve security, privacy, resolve the ossification problem, but also keep the network manageable. So that's part of the discussion here. There's one more slide. Okay, that's only the related draft. Yeah, so as I just said, this is not only about QUIC. This is really about like encryption in general. So there are different drafts in the IETF which are not, again, not always specific to a certain working group. It's really the all-over discussion we have in the IETF that provides you further big background information on these topics and these cautions here. But now I'm done.
There we go. That's the slide you were looking for. Okay, so I'm going to round this up by giving you a fairly quick tour of all the meetings that are happening in London this week. So here's all the meetings on one slide. I'm split into categories: area-wide meetings, TCP-related meetings, congestion control meetings, new protocols and deploying new protocols, and then everything else that didn't fit into one of those categories. And sorry for the acronym soup. I'll expand the acronyms on the following slides. So the first meeting is actually one that Mirja co-chairs. There's an area-wide transport area meeting, which is a venue for discussion of topics of general interest, the entire transport area. This week's primary topic is TCP encapsulation, which is you have a protocol that doesn't go through middle boxes such as NATs. You can either work on NAT traversal in that protocol, or you can encapsulate something like TCP that already goes through all the middle boxes. And the first example is that IKE, which did its own NAT traversal in UDP, is now also being encapsulated in TCP, in part because TCP is simply more robust than middle boxes. Monday afternoon. Transport Area Working Group. As Mirja said earlier, this is a catch-all working group for work that needs to be done in the transport area, but can't sustain its own IETF working group. There's a long list here. I basically pulled all of this off of the agenda. SCTP work, better support for scavenger traffic. We're doing some forward area correction work, a couple of pieces of work on UDP, the most interesting of which is adding options to UDP. Turns out we're adding them as trailer options rather than header options. Some work on ECN and L4S, about which we had some slides to say earlier, plus one of the encryption transport protocol header drafts is a discussion item in this working group. Thursday afternoon, we've actually got two sessions back to back. That 1550 to 1910 time slot is actually split over two sessions. I think we'll put a break in the middle when everybody else takes a break. The TCP work is primarily done in the TCPM working group. They work primarily on maintenance issues and bug fixes and moving TCP and TCP options along the standards track. Current topic discussions: ECN alternative backoff. When ECN is in use and giving you congestion signals as opposed to dropping packets, it turns out that you can back off by less and get more effective interaction with the network, and also improvements to accuracy of ECN feedback and a time-based loss detection algorithm called RAC. That's going to start tomorrow morning in Buckingham. Multipath TCP. TCP has run over multiple paths with this protocol for quite some time. They've got quite a bit of experience from it, so they're working on a revised standards track version of that protocol, and that'll be Thursday afternoon before TSVWG. ICCRG. Mirja briefly mentioned this. This is a research group in the IRTF that works on internet congestion control. You can think of it as an expert advice on congestion control group that advises the transport area in a manner roughly analogous to the way that the Crypto Forum research group provides expert crypto advice to the security area. London agenda. There's always congestion-related topics. BBR congestion control right now is a discussion topic in ICCRG, as this is still not yet far enough along in terms of maturity and proof that it works well and is safe to be ready for standardization. This will be Friday morning. Miria also mentioned our RMCAT. This is for interactive real-time media congestion control. The set of requirements are sort of listed in that first bullet list. They've got some congestion avoidance algorithms. One of the more interesting ones, which is called NADA. They're now working on evaluation criteria for these algorithms and how at the RTP level you ought to be doing congestion feedback via RTCP, Wednesday afternoon. Okay, so that's the first three topics. You are here. We're now going to talk about new protocols and deployment and then everything else. So the latest instantiation of the Quick Adventure is going to be twice this week, Monday afternoon and Thursday morning. The Quick protocol is very close to done, but they're living through the 90-90 rule of project management. The last 10% of the work takes the other 90% of the time. There are some security topics. They're busy writing down invariants, things that are fundamental to Quick design and simply will not change in future versions of Quick, things like the connection ID, writing down the details of ECN support. And I don't know, Mir, have they set a record for amount of time spent discussing a single bit in a protocol header? They've come close. It's a spin bit. And what this is about is, I had said some things earlier about wanting to do measurements in band so you know the measurements are tracking along the path the protocol takes. The spin bit is a single bit proposed for the Quick protocol that enables a pass observer to watch the session and understand what the round trip time is that it's seeing. Transport Services, this is the TAPS working group. They've done some work on an initial interface that's protocol independent, where the application expresses the requirements it wants. Does it need reliable delivery? Does it have time-based delivery requirements? The work now has moved up a level to Transport Service Architecture Interface structure. In addition, how to cover transport security protocols in this framework. Wednesday morning. Alto, we're now into the everything else. Application layer transport optimization. This is actually a fairly high level protocol, runs over HTTP and provides a distributed application with some indication of how the network has been structured. This is for protocols like P2P, peer-to-peer and content distribution networks, where the way you structure the entities that participate in the protocol benefits from some structure of the network in which you deploy the entities. The initial protocol work has been completed. The stuff works. It's being extended, generalization of endpoints to domains, adding some additional path information in addition to endpoint latency maps, and some other ways to extend it Monday afternoon. Delay tolerant networks. This is I like to think of it as the long distance networking protocol, but it also deals with intermittent connectivity. There was an old joke back when we first started networking that the highest bandwidth networking connection in Manhattan, or for that matter, London, was a canister of mag tapes moving uptown in a pneumatic tube. The protocols that this group develops would work over that class of intermittently connected infrastructure. The fundamental protocol they're dealing with now is the store and forward bundle protocol, where they're working on TCP details. When the forward happens over TCP, how does bundle work with TCP, plus security management topics, also Friday morning. IP performance metrics, talked quite a bit about what this was about in an earlier slide. Current work is on a core registry of standard metrics for common metrics and use cases, and that'll be Tuesday afternoon. There are also three other active transport area working groups that are not meeting in London. The first is NFS v4, which works on the network file system v4 protocol. That's a distributed file system protocol. There's a lot of details going on in there, which I'll leave you to look at the working group's charter and drafts on. TCP Inc. This is a protocol that does unauthenticated security for a TCP connection. The basic idea is that if the application doesn't have its own built-in security, it doesn't have the infrastructure to use TLS, when the application establishes a TCP connection, there will automatically be a security layer put in place that by the TCP stack that takes care of hiding this from eavesdropping. And this is unauthenticated security because it just sets up anonymously. For authenticated security, you really want to modify the application to use TLS. The work in this work group is very, very close done. In fact, just had a meeting just before this session to understand where we are in the very last issue. Disclaimer: I'm one of the chairs of this working group, so it's my responsibility to get this done. And finally, TRAM, which is working on the turn protocol for NAT traversal. There's continuing to do updates, improvements, but they don't have a need for a meeting here in London. So, acknowledgements. It takes a village to put this together. We'd like to thank all the people listed here, active in transport area, for helping us out in putting this tutorial together. And there's a brief survey. Please go to this URL and complete a very brief survey. 5 questions, 1 page. And with that, thank you very much. And Miri and I will be happy to take questions. Any questions? Everybody must still be jet lagged. Thank you all very much. We'll be happy to answer questions directly up front. Right on time. Let's slide the next victim. The slides are going to be posted.
Are they not posted?
I don't know where they're posted yet. In addition, I need to send an updated version. The posted version was about 3 days ago, and I think we've changed about 1/3 of them since then.
The general, the data tracker is there is like somewhere a point where it says meeting material. There's like
Right.
all the slides.
On the agenda page, check. Let's see. I have to send the email with the new and improved slides. But I would check, say, Monday afternoon or sometime Tuesday, and if they're not posted, and they should be posted. If they aren't posted, let's see. Does the IOC have a? If they're not posted, send one of us an email, and we'll figure out how to get them posted.
You can quickly check if they're posted.
Let me take a look here. Well, what we posted will be the old versions of them. I need to see.
Something.
Yeah, it's still something. Go have a look. All right, let's just see if we've got them. Hang on a minute.
Do you know the data tracker?
Okay, yeah. So this is the agenda page of data tracker, and it's yes, the slides are posted. That'll be a link to the slides right there. Okay, and as I said, check back later because the version they've got posted is right now an 00. You look for an 01 version, which will contain some minor updates.
Okay.
But the 00 version is not bad. It's not. We're not embarrassed by it. That's why we let them post it.
And the other one is you were talking majorly about the encryption of the transport. Is it because the transport because I'm thinking what about it when so much about encryption of the payload? The payload is actually much more important.
So, I mean, like, HTTPS has become about 50% of the ongoing work. And